Let's talk about one of the biggest tug-of-wars in tech right now. You have this explosion of artificial intelligence that is just ravenous for data. But at the exact same time, you have these global privacy laws that are putting up some serious walls. It really feels like an unstoppable force meeting an immovable object.
Okay, so let's really break this down. On one side of the coin, you have the law, and it's crystal clear. Protect personal information. No excuses. But on the other side, the very machine learning models that are changing our world, they need massive amounts of data to learn, often that same personal information. So what gives? How can we possibly innovate responsibly and fuel this AI revolution without totally compromising individual privacy? That is the big question we're going to unpack today. To get to the answer, we have to start with the rules of the road. And that means understanding the global compliance mandate, this legal framework that really sets the stage for everything else. What's really striking is just how specific these laws are. You look at the GDPR in Europe, and it's not just talking about how you store data. No, it goes right to the heart of AI, automated decision-making. This isn't some vague suggestion, it's a direct mandate for transparency, giving people real control over how algorithms use their data. And look, this is not just a European thing. Doesn't matter if we're talking about California's CPRA or China's PIPL, these core ideas are showing up everywhere. You have to tell users what you're doing, you have to get their explicit consent, your systems need to be fair, and, this is a big one, you have to be able to explain why an AI made a certain decision and give people a way to just opt out. This whole legal landscape is the why. It's the reason we desperately need new tech solutions. So, let's switch gears and look at the technical side of things. If the law is the why, then the way AI models can accidentally leak data, well, that's the how. We call this AI's inference problem. And that's a perfectly fair question, right? You'd think that once a model is trained, the original data is kind of, forgotten. But that's not quite right. The model actually keeps a memory, almost like a mathematical shadow of the data it learned from. And, as you might guess, clever attackers have figured out how to exploit this. This leads us right to the idea of inference attacks. Now, this isn't your classic hacker breaks into a database story. This is way more subtle. It's about strategically prodding and poking a model until it basically confesses details about its training data. The model itself can become a privacy leak. So, what do these attacks actually look like? Well, with membership inference, an attacker can figure out if your specific data was part of the training set. With attribute inference, they can predict sensitive things about you that weren't even an output of the model. And then there's the really scary one, model inversion, which can literally reconstruct bits of training data, like a person's face. Yeah, these are the specific threats that keep privacy engineers up at night. So we have this big legal requirement and a really serious technical risk. How in the world do you bridge that gap? Well, the answer lies in a really powerful toolkit known as privacy-enhancing technologies, or PETs for short. Now, the key phrase to remember here is data in use. We've gotten pretty good at encrypting data when it's just sitting on a server or flying across the internet. PETs are the next frontier. They protect data while an algorithm is actively chewing on it, which is the exact moment AI models are most vulnerable. Now, within the world of PETs, there are two major philosophies we're going to compare today. Each one represents a really powerful but very different approach to privacy: differential privacy and homomorphic encryption. First up, we have differential privacy. The main idea here is all about plausible deniability. By adding just the right amount of mathematical noise to a dataset, you can effectively hide the contribution of any single person. The big picture trends are still there, but you can't point to any one individual. Their privacy is preserved. Think of it like this. You're trying to hide one person's voice inside a giant cheering stadium. With differential privacy, you're not trying to silence them. You're just turning up the volume of the whole crowd so that one voice just blends in and becomes indistinguishable from everybody else. Okay, now let's switch gears to homomorphic encryption. People literally call this the holy grail of cryptography, and for a very good reason. It allows you to do math directly on encrypted data. I'll say that again. You can perform calculations on data that you can't even see. It never, ever has to be decrypted during processing. The best way to get your head around this is the locked box analogy. So picture this. Step 1, you put your sensitive data in a box and you lock it. You've got the only key. Step 2, you hand that locked box over to an AI company. They have no idea what's inside. Step 3, they use these special gloves that are built into the box to do all the calculations on the data without ever opening it. And finally, step 4, they hand the locked box back to you. Only you, with your key, can open it and see the result. The provider learns absolutely nothing. Okay, so let's put them side by side. If you take away one thing from this explainer, make it this slide. Differential privacy is all about adding noise. Its main goal is protecting the output from inference attacks, but the trade-off is a constant balancing act between accuracy and privacy. Homomorphic encryption, on the other hand, is about calculating unencrypted data. Its goal is protecting the data during processing, so the model provider sees nothing. The trade-off there? It is computationally very expensive. They solve different but related problems. So ultimately, these technologies aren't just clever math problems. They are the real-world tools that let organizations finally put a foundational legal principle into practice. And that principle is privacy by design. It's this idea that you don't bolt on privacy at the end like an afterthought. No, it has to be baked into the system's architecture from the absolute beginning. Pets are how you take that idea from a legal textbook and turn it into actual code. And you can see exactly where our two technologies fit into the 7 principles of privacy by design. Differential privacy, that's a textbook example of Principle 3, embedding privacy right into the design of the training pipeline. And homomorphic encryption, that is the ultimate expression of Principle 5, true end-to-end security, because it protects data even while it's actively in use. These are real, concrete answers to major compliance headaches. So that leaves us with this final question, and it really gets to the philosophical heart of the issue. As we build the next generation of AI, what's more important for compliance? Is it the perfect secrecy that homomorphic encryption offers, where absolutely nothing is ever revealed? Or is it the plausible deniability from differential privacy, where an individual can safely hide in the noise of the crowd? The answer to that question is going to define what trustworthy AI really looks like for years to come.